Good morning. I'm Mike Koets from Southwest Research Institute. I'm going to be talking today about communications infrastructure for fractionated spacecraft. And this work is part of a large and ongoing DARPA project, the F6 project. So I'm going to be discussing one small facet of this, the stuff we've been working on for the past 18 months here at Southwest. There are many other aspects. I'll allude to some of them, but know that this is part of a bigger project and an ongoing effort, so not all the problems have been solved. So what we're looking at is fractionated spacecraft. And in the jargon of the F6 program, what we're trying to do is replace a monolithic spacecraft, one single bus, with multiple independent free-flying spacecraft that accomplish the larger space mission collectively rather than in a single spacecraft. So there's several reasons why we're exploring this, several benefits that the program hopes to get out of this architecture. The first is to extend and enhance ongoing missions. So a mission in flight, maybe a new sensor or an improved sensor becomes available, an improved communications link, faster processors. Those capabilities could be added to the mission by launching a new small fractionated spacecraft, a small module that could join the cluster, work with it, either replace a module or be added to it, and enhance it at lower cost than replacing the entire mission. Similarly, we might be able to replace failed components. If one of the modules of the cluster fails, we'll launch a replacement at lower cost than replacing the entire mission, and possibly have the mission continue while that replacement is prepared and launched. Also, we're interested in surviving module failure. So, I'm sorry. So if there's a collision with space debris, for example, we could replace that module. But also something we hope to do with this, beyond these survivability, these robustness characteristics of a clustered approach, is spatially distributed sensing. We kind of have a very notional example in the diagram here. Dr. Birch gave a very concrete example of spatially distributed sensing this morning. But the idea is that you would like to be able to sense in one mission over a spatial region that's far too big for any single spacecraft. The notional image here is a study of the aurora. So we have an imager that will image the aurora over the Earth, but then also a cluster of 4 other spacecraft that are measuring the magnetic field directly associated with those images. Also in this example, we have a 6th module that serves as a communications relay, a sensor processing node where the data is fused, and data storage. But the idea is that by flying a cluster of spacecraft, we could gain capabilities beyond just survivability versus a single monolithic spacecraft. So in order to do this, we have a number of engineering requirements. A key one is coordinated navigation. We need to make sure that all of these spacecraft fly around and stay close to each other, but not too close to each other. So that's a major part of the program. Distributed operations of the cluster is another element. There's people working on a distributed operating system that allow applications to be programmed into clusters of spacecraft in sort of a coherent way, as if it were one system rather than 6 independent spacecraft that are just communicating a little bit. But what I'm going to talk about for the rest of this presentation is the communication between these modules. Certainly for this sort of unified view of the cluster, but in any case, all of these spacecraft need to communicate to make this cluster flight happen. So I'm going to be talking about the work we've been doing at Southwest to develop a communications link for these fractionated clusters, focusing primarily on the data link and the types of communications that are available between modules and to the software running on those modules. So we have a number of challenges in developing a communication system for a fractionated mission like this. One of the key ones is the wide variation in distances we might experience. In the missions we've looked at for this program, there's 2 orders of magnitude, from a few hundred meters to dozens of kilometers of separation. This makes the radio communications very challenging, since the amount of data we can move varies with the distance between them squared. But we'd like to be able to make the best use we can of whatever capacity we have. So at very great distances, we're only going to be able to communicate very slowly. However, when modules do approach each other, either through just orbital dynamics or through different ways the cluster may be used, we don't want to design around that worst case that works out at 100 kilometers. We want to be able to take advantage of the higher data rates that are available when they actually are closer. Problems this audience is completely familiar with is the limitations on size, weight, and power available to us, especially since we are talking about launching 4, 10 spacecraft. The amount of power available to any given radio is very limited. Also familiar to all of you is the limitations of space-qualified radiation-tolerant hardware. Whatever we design has to be able to run on the available processors and FPGAs. Something else that's proven to be extremely significant is regulatory approval for using radio spectrum in low Earth orbit. So those are challenges we have to address. We also then identified a number of desirable characteristics, things we would like to get out of our radio link to help solve this problem. And one of the key ones that we identified was predictable performance. We want to be able to at least understand, if not guarantee, what kinds of throughputs, what kind of data rates, and what kind of latencies, delays, are available for communications between these spacecraft. And because of this criteria in particular, we sort of set off on developing our own data link and our own RF waveform. We looked at some of the commercial standards for wireless networking, like it's ongoing by all of you in this room, looking at cellular standards, and nothing quite met that characteristic and really applied, we felt, well to the cluster flight problem. We also need to make efficient use of our data capacity. Because of the regulatory issues, because of the power limitations, we'll only have so many bits per second available for communications in the cluster. And we wanted to design a system that used what physics gave us as far as communications capability as efficiently as we could. Also, we wanted to design a system that was robustly tolerant to node failures. Survivability is a key motivator for this whole program. We wanted a system that did not have any special roles for any individual modules. There's no base stations. There's no central coordination. That if that single point failed, if that was the module that collided with something, then the whole network would go down. We wanted to survive that seamlessly. There's a couple other features that we figured we could add in that would be extremely valuable to this application that the radio link would give us. One is the ability to estimate the distance between modules using our communications mechanism. And then second, maybe more important, is the ability to distribute a common time reference throughout the cluster that could be used for other applications. So this is a very notional description of what we ended up with in our design. We are using a TDMA, time division multiple access burst mode communication system. Time division multiple access means that we are allocating access to the radio communications medium on a time slice manner. So certain modules are given opportunities to transmit on the channel at certain times. Other modules can't transmit then. This architecture gives us the predictable throughput and latency we're working for. Everything is scheduled. We can understand that schedule and understand when data is going to move through the network. Also, using a TDMA mechanism, as opposed to some other mechanisms that are very common in wireless networks, we have no contention for the channel. So we're going to schedule who uses the channel all the time, so we never waste time or waste capacity with messages colliding on the air. This is a fully distributed data link, so coordination is distributed evenly throughout all the modules. And this is so we can be robust to the loss of any particular node. We provide on-demand resource allocation. We don't need to pre-plan this on the ground on a roughly second-by-second basis. The access to the network is negotiated by the modules in flight. And we also provide 3 different data transfer mechanisms, which we're going to talk a lot more about in a moment. So the basic architecture is that we divide communications up into a sequence of what we call frames. Each frame is about a second. There's variation in there. But it's a period of time where data communications can take place. And it's notionally illustrated at the bottom here. Each frame begins with the exchange of some network coordination messages amongst all the nodes in the network that they use to negotiate who's going to get access to the data transfer capacity. That period of management is followed by a number of data transfer slots. So each of these slots is a period where one of these modules can transmit. This diagram is not at all to scale. The blue boxes that represent the network management takes up a very small period of the time in a frame. Most of the time is given over to exchanging data. The circular diagram there is sort of a very notional view of what how the distributed coordination works. Each of these frames, and there's an endless sequence of frames, is owned by one of the modules. And that owner has special responsibilities for the duration of that frame to coordinate access to the data transfer slots. But that ownership rotates through the modules. That's what the bigger outer circle is that as frames go by, 1, 2, 3, 4, each frame in sequence is owned by a different module. So if one of those modules were to suddenly fail, it wouldn't be able to do its job for any frames it owned, but all the other frames, other than the ones it owns, other modules are responsible for. They will continue to coordinate access, and the network will stay up and stay running, even in completely unexpected loss. So then the smaller circles in the diagram show these network management bursts that are exchanged by all the modules on every frame. And in the center, we have the data slots. And this is there to make it clear that each frame, there's a negotiation process where access to the communications channel is coordinated amongst all the modules. But on any given frame, every module can have the opportunity to transmit regardless of who the owner is. So this is not a token ring system. And that's an older networking technology, predated Ethernet, where opportunity to transmit slowly rotated through all the members of the network. And if you happen to need to send data at the wrong time, you have to wait for many, many frames before you had a chance to transmit. We're much more responsive to that, and our latencies are much lower. So this is the first of the transfer mechanisms that our data link supports. Now these transfer mechanisms are available to higher network layers. These are the communications primitives that the software running on the different modules of the cluster can use to move data. And the different mechanisms have different characteristics as far as throughput and latency and determinism that are tailored to different applications the cluster might be executing. So the first of these is a generic. And I'm going to show 3 slides, and they're all going to look very similar. What we have here is each of these rows is a frame, and we have a sequence of frames moving down. User data is provided by some node of the network into the data link, and then the green boxes show how that data flows through the network in time. Generic transfer is a best effort transfer mechanism. This utilizes all available capacity in the network. This mechanism fills in any gaps we have. We never have the channel idle unless truly nobody in the network has any data to send. A key thing for the generic link, but also for all of the links, is that we can multicast data at the data link level. So a sender can indicate which other modules the data is intended for. And if it's intended for multiple modules, we'll just address it appropriately and send it out in a single broadcast. So we don't need to use up network bandwidth retransmitting a message if it needs to go from one module to several others. This is generally the highest throughput mechanism because it can use up whatever capacity is available. We don't provide latency guarantees on this, though, because it is a best effort, because it's using up whatever capacity is there, we can't really predict what the latency is. So the idea here is this is bulk transfers, things that are not time critical, but maybe large, moving sensor data around, moving anything that doesn't have strict deadlines. The second communications mechanism is what we call the isochronous transfer mechanism. Again, this is the same idea. This is a sequence of frames. And with the isochronous mechanism, one of the slots in each frame is reserved for long-term use by a single node. So it's a long-term capacity reservation. This one does have guaranteed latency. A user of this link will know that it has access to certain frames at certain times in perpetuity. There's no ambiguity about when their next transmit opportunity will roll around. So it also provides precisely scheduled delivery. So not just latency, but you know exactly when data will show up. So this is a useful mechanism for things like streaming data that are where data is being generated at a very regular rate, but also for things like distributed control loops, where perhaps for some reason one module is sampling some characteristic and another module needs to use it in a closed loop, precisely timed situation. If that timing is off, either too early or too late, the control loop might not work well, or may need to be designed to work less well to be robust to those circumstances. But here we provide very precise timing for that. Also, just any periodic data with strict latency requirements, this mechanism is a good way to handle that. So the final transfer mechanism is critical transfers. This is a minimum latency transfer mechanism designed for infrequent but mission-critical communications events. The way the critical transfer mechanism works is you have guaranteed access to the absolute next data slot that rolls around. So as you work through these frames, data comes in, first slot of the next frame, it can go out. If it happens that multiple modules try and send critical data at exactly the same time, there's a prioritization mechanism to resolve that. Everybody gets it out pretty quick. The first person in gets that access to that very first slot. But the idea here is that if you have data that has an absolute minimum latency requirement, this is the mechanism to use. The motivating example, going back to the program objectives of the larger F6 program, was hazard avoidance. One of the goals of the program is to have the ability to command all the modules of the cluster to move a certain distance away from their previous position, their previous orbital path, in a minimum amount of time. The longer you wait from when you need to tell the modules to make that move to when they need to be moved away, of course, has profound impacts on the fuel budget. And so we want to be able to move those commands very quickly, very minimum latency. So that's the motivating case for this data link, or for this mechanism. But there's many other cases. One is sensor queuing. If you have one module detect an event and a sensor on another module needs to respond to that event in real time, this mechanism can be used to transfer that queuing to the other module. I did want to talk briefly about the physical layer waveform, the actual signals that we're sending, because it informs some of the other data link aspects of this. We're using a wideband direct sequence spread spectrum signal, which is not, it's related to contemporary cellular data signals. We use a scalable data rate that varies with distance. So like I mentioned, one of the key considerations of this was you may have a wide range of different distances between modules, and we want to be able to communicate efficiently at whatever distance we're at. This may change quite a bit over the course of an orbit, certainly over the course of a mission. So this waveform lets us scale the data rate to move data as fast as we can, given the distance between modules at the current time. Now this waveform does require fairly precise time synchronization between the sending and receiving modules. So we put a great deal of our research into developing specialized algorithms to let us achieve that time synchronization between modules, maintain it over the frames of the communications. We get some side benefits from this synchronization, though. We can use that precise time synchronization that we need to communicate anyway in order to estimate the range between modules, one of the desirable characteristics we talked about, but also to transfer time amongst the network. We can bootstrap that too to guarantee that we have a very precise, common clock distributed throughout the cluster, and precise beyond the ambiguity of their distances. So in addition to the data transfer mechanisms I talked about, we provide a few other supporting services that help with the cluster flight application. We provide intermodule range estimation, which uses the physical layer. This is completely independent of GPS. Many of these systems, you can imagine flying GPS receivers on all the modules, and that will be a better estimate of position. But if one of those were to fail, or if cost or size constraints prohibited including a GPS, you can use this mechanism to very accurately estimate the ranges between modules and then get a larger view of the cluster geometry. Our system gives you accuracy at about plus or minus 6 meters. And we distribute that information throughout the network automatically without using up any of the data capacity of the network. We also distribute the common time reference. Same thing, utilizing the physical layer mechanisms. We can use this to timestamp range measurements, which are really needed for cluster navigation, timestamp sensor measurements, packet data. And as a third service we provide is link layer topology monitoring. We monitor and distribute throughout the network all the links available between pairs of modules. And this can be used by higher network layers to help with routing data through the network. So just a couple of quick slides on performance. Like I said, efficiency was one of our key drivers in our design. And so this is an analysis of the overhead of our network. There's several configurable parameters that affect overhead. One is the network population. The more nodes there are in the cluster, the more spacecraft. There's a little bit of a hit on overhead. Data slots per frame is another configurable parameter. The more data slots you have in a frame, well, the longer the frame is, but you only send the network management information once per frame, and so you do increase your throughput. You spend less time just running the network, more time sending data. The cost of that is increased latency. Because access is negotiated on a frame-by-frame basis, if you pick the wrong time to ask for capacity and you have very long frames, it might take longer before you get that chance to send that data. A third configurable parameter is the max operational range. We have a variable or a parameter that sets how far away you expect most distant two modules to be. That'll let us tune the system a little bit to take advantage of that knowledge. So if they're going to be 30 kilometers apart, that's fine. We'll set the parameter there. But if they're really only going to be 1,500 meters apart, well, we can tune it for that and get a little bit more out of the network. For the data I'm showing here, we've set that to be about 8.9 kilometers max operational range, which is fairly large for some of the cases we're looking at, but obviously not as large as you might go. The plot then shows overhead in percentages. X-axis is the number of modules in the network, and then each of the traces is a different number of data slots per frame. Clearly, it increases with the number of modules. Increasing the number of data slots per frame brings your overhead down. Overhead here is all of the time, real time, that we aren't sending user data. So this is all the overhead, any negotiation, any padding we need between bursts, warm-up time for transmitters. Everything where you're not sending actual user data is overhead in this analysis. And so we can get as bad as 20%, but we really don't recommend you'd operate the network at that configuration. Generally, we're below 10 in many cases, so fairly efficient overhead. And also interested in throughput. How much data can you move through this network? That's shown in this plot. Much of the same parameters hold, 8.9 kilometer operational range. X-axis is the number of modules. Each of the traces shows a different number of data slots per frame. Data rate automatically scales with the distance between the most distant pairs of communicating modules. So when you're sending user data, if you address it to a specific module, and that specific module is distant, you'll send it at a slow data rate. If the specific module is very close, you can send it at a much, much faster data rate. And for this data, that's true even if there are other modules more distant. The more distant modules won't hear it, but you never intended them to anyway. That's all built into the network. So you can scale the data rate exactly as you need to get the data where you need it to go in the cluster. Throughput here is the total user data capacity. You can see, I'm sorry, I misspoke. The x-axis here is the intermodule range, the distance between communicating modules. So you can see the data rate, as physics demands, falls off exponentially as you get more and more distant. However, we do send the data as fast as we can given the distance we do have. We do pretty well, especially at short distances with several megabits per second of user data available. So I'm running low on time, but I want to talk very briefly about the software development process we used. Again, this was motivated by the way this project was run, which had a very strong emphasis on continuous integration, frequent demos. We need to be bringing this capacity up very incrementally and starting to tie it in with other aspects of the program, the operating systems and the applications that were being developed to run on these spacecraft clusters. So the progress is shown from top to bottom. The orange boxes represent the data link layer software written in C++, and that's common throughout all of this. We wrote it early, most of it early, developed it, but kept this common code base flowing through this development process. At the very beginning, everything's running on a single PC. We have multiple instances of our data link. We have a radio emulator that simulates all of the real-time and over-the-air traffic. And we have message traffic, sources and sinks, all running in software, single application running on a PC. But it starts to exercise the data link software, allows us to integrate with other aspects of the program. Moving on, We took that software, we ported it to our target processor, which was a UT699 running RTEMS, brought it onto there, onto a couple of evaluation boards for the processor, connected those via SpaceWire to message sources, message sinks, and then also by SpaceWire to a PC, which is still running this radio simulator. We still don't have radio hardware available. But now we're increasing our fidelity. We brought our code over onto our target platform. Again, we can continue to integrate with other aspects of the project. Now, finally, we're getting to this point. We have message sources and sinks on a PC. We've moved everything onto our own custom hardware, which includes the UT699 processor, as well as the Xilinx FPGA and RF electronics. So this is all running on terrestrial prototype hardware headed towards spaceflight. Again, we're still running the same code, same integration, same API. This has been a useful, if somewhat challenging, development process. We had our code up and running early, quickly. We found lots of our problems, got things going. So it's been an interesting development process. So just to summarize, F6WIX, which is the name of our radio link, communication system tailored to meet the very specific needs of communications in a clustered flight mission. We provide these 3 different data transfer mechanisms with well-defined and guaranteed characteristics that the applications running on the cluster can use to meet the application needs, to address throughput, timing issues, latency issues. We have a physical layer waveform that provides services that support this fractionated spacecraft cluster flight application, ranging, time transfer. So this design is now being implemented on the terrestrial prototype hardware. It's happening across the street as we speak. And current plans are to have an on-orbit demo mission of the F6 cluster concept in a couple of years. So brief acknowledgement, the work was fully supported by DARPA, and a couple of disclaimers they requested in there too. So and that's it. And don't have much time, but I'm happy to answer any questions. Yeah?
Can you go back to the slide that showed the effect of the number of nodes on the overhead? Yes. Mm-hmm. How do you get linear scaling with quadratic links among? You have a quadratic number of links, right?
Yes. But it does scale linear because the effect on overhead is each module has to send one of those network management bursts, but it is multicast through the whole network. Those data rates are tuned so that so they can reach everybody. So that scales linearly with the number of nodes.
I found this presentation very interesting. I'm a PhD student, and my area of research is distributed wireless systems and communication. So a lot of these charts and graphs are familiar. You mentioned that a lot of research went into figuring out the time synchronization and when to send and receive. I was wondering, have you looked at a lot of stuff from the wireless sensor network community, things like MAC protocols, routing, flooding, things like that? Have you read, was that a focus of your research?
The research we did was at a finer grain and a lower level. We were looking at the nanosecond, basically, timing synchronization we need to lock up to the direct sequence waveforms. So we're looking at aligning at a very, very fine time-grained within a single communications event. And a lot of the research went into fitting that on an FPGA that's practical.
So your methods then are more closely tied to hardware rather than software.
That's right. Because we needed that time synchronization for the waveform, we could leverage it to replace some of the MAC level time synchronous distribution you're talking about.
Okay. And then I have 2 other questions, if you want. One of them is, as the nodes communicate with each other, do you utilize any type of security?
That's handled for the user data. That's being handled by other developers within the project. It's a major concern for this project, and as people spending a lot of time looking at it. We do have the ability to scramble the network management data, the stuff that's not controlled by the higher layers. We don't run the details of that. We query the higher layers for the scrambling strings that they'd like us to use, so that security can be handled as a central aspect above our layers.
And then the last question was, you talked earlier in your presentation about what happens if a node goes down and then his responsibility might be distributed amongst the others. What about a node coming up? Do you have
Kind of both. As you add a new node to the network, yes, the network can easily be reconfigured on the fly to grant it permission and bring it into the communications. We do require that that be authorized by a higher entity who has the authority to allow a new network in or new node in. One of the things we were very consciously trying to avoid was to have some rogue spacecraft get close enough to communicate and suddenly be in the network. We wanted to make sure that was a very authorized process and that couldn't happen by somebody who was trying to gain entry into the network.
Thank you.
A couple of clarifications for a couple of answers that you gave to gentlemen over here.
Mhm.
So you're saying that security only can be handled at upper layers. So physical layer security, physical layer attacks are not handled currently.
So we have a fair amount of transect security built because of the nature of the waveform. It's a very wideband direct sequence. But beyond that, yes. I mean, we do not have special characteristics to address things like jamming.
So, and the other thing that one of the answers, like you mentioned, that all of the research that was very specific to firmware and not software.
I'm sorry.
The research was targeted to firmware implementations only.
No, the implementation of this is distributed between software and firmware. The low-level signal processing and the very low-level time synchronization is in firmware. But most of what I talked about with the different transfer mechanisms and the link coordination.
The timing is done.
Right, and the modem, the signal processing. All right. Thank you.